Today on the podcast, we're going to cover the recent paper in Nature by Daniele Leonori and his group. The paper is a photochemical dehydrogenative strategy for aniline synthesis. And so in it, they disclosed a new method for making anilines in which you're no longer doing some sort of substitution on an aromatic system, but instead accessing them through dehydrogenation of saturated cyclohexanes. We'll start kind of by going through a history of aniline synthesis, a brief history of aniline synthesis, and then really get into this paper and kind of the unique dual catalytic process that comes from a photochemical and hydrogen evolution catalytic approach.
Yeah, so if we think about the modern methods to make anilines currently in the literature, one might look towards cross-coupling approaches. And there are several ways to cross-couple an arene with an amine to form your aniline, but they all proceed through some sort of functionalized aromatic group. So starting with an aryl halide or an aryl boronic acid, which then can oxidatively add to your metal. And then upon coordination of the amine, can reductively eliminate and form your product. Having to use a aryl halide or aryl boronic acid introduces a limitation in this approach, since if you have a pre-functionalized arene and want to strategically add your amine to a certain position on the arene, so either ortho, meta, or para, in order to install that halide or boronic acid, there's limitations in the methods to do that.
So the typical way that you'll try and even make some of these starting materials that you would want for these cross-coupling. So for example, aryl halides is through traditional electrophilic aromatic substitution chemistry, EAS chemistry. And those have inherent electronic limitations when you're starting to do that substitution. So if you have a electron donating group on the aromatic ring, then you're favoring that substitution at the ortho and para position. And if you have an inherently electron withdrawing group on the aromatic system, then you're going to favor the meta position. And if you have competing or more electron neutral aromatic rings, then it gets really difficult to select for one of those positions. And so you end up instead having to go through and separate out mixtures of those systems or try and do the reactions through different ways, which can typically be very steppy. In a similar manner, the boronic acids, to try and make a boronic acid, you typically have to do some sort of organometallic species that allows you to access a boronic acid. And those are typically controlled through steric means or through directing groups. And so again, you kind of typically have to have a more steppy process to try and get at these these substrates that you're then going to try and use to make these anilines. And so developing methods that can remove that need and allow you to basically target any position on the aromatic ring that you would want to use to make an aniline is a benefit to basically the synthetic community.
And I think the bottom line here is that if you have the aryl halide or aryl boronic acid that you want along with the amine, the cross-coupling chemistry is pretty robust. The Buchwald-Hartwig reaction is really good, but it can be tough to get to that aryl halide or aryl boronic acid. Another approach that people have taken is to use an unfunctionalized arene, hoping that if you go away from a functionalized arene, you can remove that problem. So over the years, a couple of different approaches have been published here. One of the most notable ones was from the Nasevich group, where they used a photoredox catalyst to oxidize an electron-rich arene to the radical cation, and an amine nucleophile could attack that arene, and you could get an aniline from that. This was also limited because attack of the amine usually occurred at the para position. So if you wanted attack at the ortho or meta position, that wouldn't work through this method.
Another method that had been developed and actually was developed by Leonori and published last year was a method to get at basically the nitrogen-centered radical of an amine. Through making a chloroamine and then protonating the chloramine and then doing a photochemical oxidation, you got to an aminium radical cation that would then undergo more traditional EAS chemistry or something like an EAS chemical reaction at a aromatic ring to eventually give you an aniline. And in that case, the selectivity for that substitution ended up being very, electronics driven, as you would expect for traditional EAS chemistry. So again, the substitution that you have around those systems really mattered a lot more than being able to choose the position that you want and just be able to pick the position that you want to have an amine at.
Yeah, and if you want more information about the Leonori paper that was published last year, we did a episode of the Cycle Edition on it. So you can find that on our YouTube channel, titled The Photochemical CH Amination Through In Situ Chloroamines.
And I think what this shows is that these general methods are really complementary, but both have their own limitations. Photoredox methods, where you can use unfunctionalized arenes, are obviously nice because you don't have to worry about making an aryl halide, but the selectivity in the reaction is very limited. Whereas the cross-coupling approaches are really robust, but you need a pre-functionalized amine. So that's where this paper really comes in, is they're looking for a solution that is robust, like the cross-coupling methods, but gives an alternative to the aryl halide synthesis. Or one of the key advances here is using a pseudo aryl halide, which in their case is a cyclohexanone, to do this pseudo cross-coupling.
So as Matt said, the cyclohexanone can basically act as a pseudo aryl halide or as an aryl halide surrogate. And basically what that means is that instead of having to do EAS chemistry or some sort of organometallic transformation to access the different on a preformed aromatic ring, instead you can start looking at potentially enolate chemistry to access maybe the alpha position of the cyclohexanone, or enone chemistry to access the beta position, and even a Diels-Alder reaction to access a few different positions where you could insert different functionality into the cyclohexanone ring rather than having to do some sort of EAS chemistry. And so what that allows is you to basically preform this cyclohexanone ring. They do also show that this works on a cyclohexenone as well. So after a Diels-Alder reaction, you can sometimes even just have that alkene still sitting there. And then what you do is you condense that cyclohexanone with an amine, some sort of primary, secondary amine, even ammonia, to give you an enamine intermediate that can then be oxidized by a photocatalyst and then continue down an oxidative dehydrogenation with a cobalt-oxime catalyst that is well known to the solar fuels field in terms of hydrogen evolution and is known to produce hydrogen when you kind of provide it with the electrons it needs to do so. So basically what you're able to do is take the cyclohexanone that you've now turned into an enamine, and after the full desaturation, you're left with a fully unsaturated aromatic ring with an amine off of it. So now you're left with an aniline that you've produced through these functionalizations, followed by the desaturation chemistry.
This idea is really building off of work that was done a number of years ago by UW-Madison's Shannon Stahl and his group, where they applied a very similar strategy for the synthesis of phenols. So they identified that, like Wes was saying, it's very easy to functionalize every position of a cyclohexanone through really well-established, really good, reliable chemistry, whereas it's hard to functionalize phenols. So if they could start with a pre-functionalized cyclohexanone and then do a successive dehydrogenation, that would be a really nice synthesis for phenols. And this was a science paper published back in 2011, and it's pretty standard Stahl oxidation chemistry. So in the science paper, the group starts with a palladium-2 catalyst, which can undergo CH activation with the cyclohexanone. And after beta hydride insertion, you get to a cyclohexenone, which after another round of CH activation and beta hydride elimination, you get to a dienone, which can tautomerize to a phenol. And that palladium-0 catalyst then can be turned over with molecular oxygen to regenerate the palladium-2 catalyst.
And this was really a key advantage to this method, was adding molecular oxygen as the terminal oxidant, because it allowed for a broader substrate scope and a lot milder conditions. And so this strategy had been applied to this sort of synthesis of phenols from substituted cyclohexanols previously, but those methods were very limited in stoichiometric substrates, harsh reaction conditions, very high temperatures. And so Shannon's group was able to identify a method to use molecular oxygen instead, which allowed them to apply this to a variety of, or to showcase this method with a variety of substituted phenols.
And one of the things that I think about, or that I think is interesting, Leonori, states this pretty explicitly in his paper that they were inspired by Stahl's chemistry to try and pursue some of this work, and others have as well in attempts to form anilines. And I think we'll talk about this a little bit more later. But just the fact that in Stahl's case, he can use molecular oxygen as his terminal oxidant. In photochemistry, oxygen is typically thought to be not as useful in that regard, as it typically will deactivate your photocatalyst and not allow you to have productive chemistry. One of the bigger insights I think that comes out of this paper is the use of protons as the terminal oxidant. So you're using them to then produce hydrogen as your final reduced species in the system.
And Wes, you just mentioned that other people have tried to apply a similar strategy towards the synthesis of anilines, and this includes Shannon. He had tried to use this strategy of using palladium and molecular oxygen to synthesize anilines from these cyclohexanones. But initially, they tried a one-pot condensation reaction followed by palladium and O2, and they said they found, or they got a mixture of products. They also said they didn't think that using a cyclohexanone and ammonia would be a favorable reaction. And so at the time, with those insights, they looked towards another method to synthesize anilines, and they ended up using an oxime approach, where now the palladium will insert into the NO bond, and this also serves then as your internal oxidant, which therefore they were successfully able to make anilines using this oxime approach.
I wanted just to point out that this reaction actually has a name. So it's one of the many named reactions. It's the Semler-Wulf reaction. And so this was one of, I believe, the first examples of a catalytic Semler-Wulf reaction to yield anilines through this method. And so that was a really nice way. Kind of building on this, a couple of groups after Stahl had disclosed this method went forward and was able to show that a more heterogeneous catalyst, so palladium on a surface, was able to do the same Semler-Wulf rearrangement in a catalytic sense using the nitroximes to produce anilines. But they followed that up with, or the group of Yamaguchi was able to follow that up and actually use ammonia, aqueous ammonia, with this heterogeneous palladium catalyst to do a aniline synthesis using hydrogenation chemistry as the method. So it's more similar to what we're going to talk about when we go through Leonori's paper. What they do in this paper is they basically dehydrogenate the enamine, the ammonium condensed cyclohexanone, and use styrene to intercept the now hydrogenated palladium catalyst. And so they end up forming ethylbenzene as their terminally reduced product. So they basically use styrene as their terminal oxidant. This allowed them to build a reasonable scope of primary anilines, but their functional group tolerance was pretty poor just due to the fact that the reaction had to be run at 120 degrees Celsius. And so I think what we'll find as we go through Leonori's manuscript is that he was able to really kind of address a lot of the different concerns that come out, or just the different problems that all of these different publications have kind of run into, which is the ability to use a primary, secondary amine and ammonia without the need to do, say, like with a Semler-Wulf reaction, or the need for some of these more harsh conditions through the use of photochemistry.
So looking at the mechanism of the Leonori reaction, it starts with a traditional condensation of an amine onto a ketone to give an enamine. And then an excited photocatalyst can oxidize that enamine to an enaminium radical. This is also pretty well precedented. So some of the early work from Macmillan did this chemistry, and Melchiori has also done some of this chemistry. And from that enaminium radical, the proton is significantly acidified. So with a mild base, you can deprotonate it to get to a beta-enamine radical. And the new part here is that that beta-enamine radical is trapped by what the authors proposes a cobalt-2 catalyst. And after beta hydride elimination, you can get to a dienamine and a cobalt-3 hydride. In chemistry that we'll talk a little bit more about later, that cobalt-3 hydride can be protonated, liberating H2 and getting you back to a cobalt-3 catalyst. And then to turn over the reduced iridium photocatalyst, the cobalt-3 can be reduced back to cobalt-2. And then basically you can go through another cycle of radical formation and then radical trapping to get to the aniline.
Yeah, and so overall, basically the reaction, you basically turn the photocatalyst over 2 times to get all the way down to the product, as well as the cobalt cycle. And so for one substrate, you end up producing 2 equivalents of hydrogen gas through the use of that cobalt catalyst. There are a couple of interesting things, and Leonori is one of those scientists who does a lot of the control reactions that we want for these sorts of papers. And so he did a lot of the mechanistic characterization that you would hope for when you're looking at one of these reactions. And just a couple of the things that kind of caught me was this idea that the oxidation of the enamine is around 500 millivolts versus SCE. But if you look at the product, so the formed aniline, that oxidation potential is only 400 millivolts more positive. At around 900 millivolts. And so that's a small window within to work where, if your photocatalyst oxidation potential or any other oxidation potential that you can have access to in that catalytic cycle is above that 900 millivolts, you're going to potentially start degrading the aniline that you form. And so, he kind of has to thread the needle here, and he's able to do that with this iridium photocatalyst, where its excited state oxidation potential is 650 millivolts or so. So you have a driving force to oxidize the enamine and probably the dienamine as well. But it's 400 millivolts uphill, 300 millivolts uphill for that oxidation of the product. So Leonori goes further than just looking at the oxidation potentials of these systems, but also looks at or does a Stern-Volmer analysis of this reaction mechanism. And so what a Stern-Volmer analysis is basically looking at the emission of your photocatalyst and watching basically at how the different additives, your substrate, your other catalyst, your base, affects that emission of the catalyst. And so that emission basically correlates to the reactivity that you're getting from the photons that you put into the system. And so if you decrease the emission, then most likely you're undergoing some sort of reaction between the photocatalyst and that substrate. And basically what he shows is that the enamine, the DABCO base, which is the base that's used to deprotonate the enamine radical that's formed, and the cobalt-oxime catalyst can all quench the photocatalyst, but at different rates. So the cobalt-oxime is about an order of magnitude slower than either the enamine or the DABCO. And because it's there in a catalytic amount, it most likely isn't a productive quencher under reaction conditions. Whereas the enamine is basically the best quencher, since it's there in a full equivalent and it has one of the fastest rates of quenching. It is going to be the major reaction pathway, and that's why they're proposing it here as the major quenching pathway of the excited state photocatalyst. And so I just really appreciated the fact that, rather than just pitching a mechanism that makes sense, Leonori went through and really shows how this reaction is working. And it just helps support a lot more also the cobalt mechanism as well, where you need to be able to access this beta-enamine radical to productively engage that cobalt hydride catalysis.
So another piece of this mechanism that I thought was really intriguing the first time I read through this paper was the fact that they said that this beta-enamine radical can be trapped by a cobalt-2 catalyst at diffusion-controlled rates and then undergo beta hydride elimination to release the dienamine and yield the cobalt-3 hydride. And looking briefly into these catalysts, and these cobalt-oxime catalysts have been demonstrated previously in hydrogen gas generation from water splitting. And water splitting is one of the holy grails of the 21st century, splitting water into hydrogen and oxygen.
And the authors of this paper say they use some of the insights from water splitting research here. So What Grace was getting at, one of the insights is that if you get to a cobalt-3 hydride in the presence of an acid, you can expel hydrogen gas and get to a cobalt-3 catalyst. So a lot of the research, a lot of the fundamental research that's been done on these cobaloxemes was applied here. And another interesting tidbit I think that I learned in reading about this is that cobaloxemes are studied a lot because they are sort of vitamin B12 analogs. So we know fundamentally a decent bit about them.
So one of the things I really liked that I kind of learned as we went through kind of learning about these cobaloxime catalysts, and some of this comes out of Jill Dempsey's accounts of chemical research article, where she really details all of the processes that these cobaloxime catalysts can potentially go through. Unlike you would kind of think of maybe a palladium 0-2 catalytic cycle, where you can just continuously go through oxidative addition reductive elimination steps or things like that. These cobaloxemes have a bunch of different pathways that they might be able to go through in terms of how you eventually get to a cobalt hydride, and then how you release that molecular hydrogen, either through, say, protonation of that hydride, but there are other methods as well where you might be able to homolytically cleave that cobalt hydrogen bond through, say, an HAT reaction. And this was actually proposed in a Nature Communication article by Eric Sorensen, where they basically looked at doing a dehydrogenation of cyclohexane, where they did an initial hydrogen atom transfer using tetra-N-butyl ammonium decatungstate, which after photoexcitation is a pretty good hydrogen atom acceptor, followed by intercepting then a carbon-centered radical through another HAT mechanism with a cobaloxime. And then they propose that to evolve hydrogen, they actually do a kind of like dual hydrogen atom transfer between the decatungstate and the cobaloxime. And so what it really just got me thinking about is if there are these many different pathways that are open to the cobaloxime catalysts, whether or not there are ways that, there are new chemistries that we may be able to access with these catalysts as we start playing around with redox potentials and the types of protons, the acidity of the protons that we have around in solution. So I think there's more that we can learn from the solar fuels field as we start applying these more towards synthetic chemistry.
So jumping back into the paper, they demonstrated the utility of this method while working alongside AstraZeneca, the pharmaceutical company. And they first demonstrated several different amines that they could tolerate in this method. And so they first focused on the piperidine core, because that's the most prevalent heterocycle present in many of the top pharmaceutical compounds on the market. And typically those are substituted at the C3 or C4 position. And so they were able to demonstrate a variety of different amines that are tolerated in this method. They also showed other functionalized heterocycles like piperazines and morpholines and prolidines. And they were able to demonstrate a broad functional group tolerance, tolerating free alcohols, esters, very electron rich groups, and electron poor functionalities. A couple substrates to highlight are this cyclobutyl substituted amine. Since if you were to try to couple this amine to form an aniline under the radical functionalization approaches, you would most likely get ring opening of the cyclobutane, or this fluoroalkylamine, which would require quite forcing conditions if you were to form this with traditional cross-coupling approaches.
So then they move on to the cyclohexanone portion of the scope, and they really emphasize that they can tolerate cyclohexanones with substitution at the alpha, beta, and gamma position, because those positions correspond to the ortho, meta, and para positions on the aniline product. And again, like Wes was saying, they underscore the ease of access to the cyclohexanones with differing substitution using enolate chemistry for alpha substitution, conjugate addition for beta substitution, and either a Diels-Alder cycloaddition or Robinson annulation for the gamma substitution. And again, the scope here is really fantastic. They can tolerate substitution at all these positions. They can tolerate pretty labile functional groups. So really not many limitations to the scope.
I think the scope also points out how complementary this method is to other approaches. So at the beginning, we talked a lot about EAS chemistry and the limitations present when trying to halogenate electron-rich or electron-poor aromatics. So if you look at product 53, that it is an electron-rich aromatic group. And if you were to use the ester substituted arene and want to install your amine meta to that position, it would be really hard to install that halide at that position. But using this strategy, you're able to access a product like this in very high yields. This is similar to electron poor arenes and functionalizing the para position. And so if you have the electron poor arene and you're wanting to install a halogen at the para position to further or to undergo a cross-coupling strategy to form your aniline, that would be very difficult to install that halogen. But using this approach, you're able to access these electron poor para substituted arenes.
Well, I think the one substrate that I really liked here that really sells this is substrate 64, where you have a cyano group that's ortho to a CF3 group in the final aniline product. And so if you think about trying to do some sort of EAS substitution there, you really would not be able to predict. You wouldn't be able to get a very high selectivity for any of the other the other two positions on that ring for installation of a halogen. And so the fact that they can get perfect selectivity for the meta position to that cyano group and pair it to the CF3 really is really unique.
I really like that you mentioned that substrate, Wes, because in their SI they mentioned how they use the Daniszewski diene to form it, and I'm not sure that everyone is aware. Daniszewski's diene is basically a very electron-rich diene, and so it reacts with very electrophilic dienophiles, which we would have in this case. And you can align the partial charges of the dienophile and the diene to predict the selectivity that you're going to see in the reaction. And so I think in this case, they were able to get a very high selectivity for the 4 substituted CF3 versus the 3 substituted cyano group to give that cyclohexanone. This diene has a masked ketone, so you start with a TBS protected alcohol. You can deprotect that to yield the ketone.
Another thing I like about this scope is the fact that they show heterocycles and basically cyclohexanones. So now having 1 degree of unsaturation added to the cyclohexanone ring, they show that they can start kind of halfway through the process and still form anilines in relatively high yield. And they do this. One of the real things I like about Leonori's scope is how complex he just kind of starts with the substrates. And so, instead of just showing that with cyclohex, he decides to do it with, a pyridine attached or thiophene. And so he shows all these different heterocycles that are also available, but also shows, this idea that he can start halfway through the process and only need to do 1 dehydrogenation to get back to the aniline. To end his scope, Leonori, I think, does what, or at least for me, was one of the most impressive parts of this, which is he just uses ammonia to go on and form primary anilines. So, an NH2 added to an aryl ring. And so just using ammonia and methanol in this reaction, he's able to, undergo the exact process. And so again, instead of just doing this on the parent substrate, he decides to add ammonia to natural products and complex molecules.
I also really liked how he showed a cost analysis between using this method on simple terpenes to substantially increase the complexity of the molecule. So he started with some simple terpenes that are commercially available and quite frequently used, like menthone, which sells for about $1 per gram. And then using this method to aromatize the ring and form the aniline, this molecule that is produced at the end of the reaction sells for $850 a gram. And so this allows you a simple way to access a structure like this in a 1-step procedure.
to wrap up his scope, Leonori does kind of two things. One, he shows that you can do a simple aldyl addition to a cyclohexanone, which leaves you with a free alcohol. And when you undergo this photochemical dehydrogenation dual catalytic reaction, you end up removing that alcohol group, but still make the aniline in this reaction. So it's a way to add functionality through that reaction. One of the founding or foundational reactions, I think, of organic synthesis. And then he goes on to basically just kind of talk more about thinking about this methodology in more of a retrosynthetic means, and really focusing on where this reaction fits in a broader picture in terms of medicinal chemistry and total synthesis. And so what he does is he shows how this dehydrogenative formation of anilines can be used to access medicines that are on the market today. He shows how you can use this method to make lidocaine and 8 other of these medicinal products. And so I think that was really impressive. And what he kind of says, and what I think is really unique about that, is he doesn't claim that this is the new method to do it, but he shows how it's an orthogonal way to think about how you might make these. So this is another tool and just another reaction to remember the disconnection of that. Basically cyclohexanone and an amine can be a disconnection for forming an aniline rather than a cross-coupling reaction. And so I think that's a really powerful way that he shows that in this paper.
Thinking about this method broadly, in the introduction, they really sold this as a new methodology for accessing anilines. And I think generally when we're evaluating synthetic methodology papers, one way to look at them one way to assess the impact is to ask whether this new method will actually be used by others to make new molecules. And clearly in the scope, we can make a lot of different types of anilines with this approach. And a lot of times I think it's complementary, like Wes said, to the other methods that we have. But even just looking at the reaction conditions, I think that this could be really quickly and easily applied to medicinal chemistry to make anilines. Iridium is a fairly expensive photocatalyst, but it's definitely in medicinal chemists' toolboxes. And if you really wanted to cut costs, I think you could probably optimize this around a cheaper organocatalyst. The cobalt catalyst is not super expensive. I'm not super familiar with these, but they seem like they're pretty easy to make. I found an undergraduate lab course that was making these cobalt oximes, so they can't be that bad. So the reaction conditions really don't seem that bad. I mean, if I had to make an aniline that couldn't be made through a Buchwald-Hartwig examination, I think I'd probably give this a try.
Yeah, I think that's like probably one of the more powerful things that comes out of this is just the fact that, with the way that I think a lot of even academic synthetic labs are, or at least where they're going, having access to an iridium photocatalyst and a cobalt oxime or being able to make them is probably feasible. And, especially if you have any sort of photochemistry project going on. But outside of that, the reactivity is mild. And, if you need to put an amine somewhere that you don't want it to be, or, that it doesn't want to go through other means, this is going to be one of the few methods you can use to do that. Well, I think this also is kind of interesting, looking towards other things than, my background is not really in synthetic chemistry, though I'm trying to make it that way. But I really want to think about where these sorts of desaturations might come into play in other reactions, where you may be able to install a nitrogen, access something that's easy to oxidize, and go through a full desaturative process. I think that this is and I like how it builds on prior knowledge. It builds on Stahl's work. It builds on these other groups' work, and it is now bringing a lot of that work into accessing even some really impressive reactivity that I think can be useful going forward.
Yeah, I agree. I think the chances that this is a one and done paper are very small. I think there are a lot of exciting ideas that could come out of this, and I'm really looking forward to seeing what those will be.
And that's our show. Thanks for tuning into this episode of the Cyclo Edition. For more information on the papers discussed, we have included a selection of resources we used in our research at the end of the YouTube video. This was our take on a very interesting paper, and we would love to hear from you. Please comment below the YouTube video and reach out on social media. You can follow the Cyclo Edition on Twitter, where we will post updates about our next episodes. If you enjoyed this episode, please like and subscribe.